I just
Torque analysis.
right. So we have done a few questions from Torque. Let's do one more problem. So basically, this is the three-dimensional structure which you need to look this way. Sorry, so it is something going this way. So you can imagine this is three-dimensional shape, something like this.
Sir, I didn't understood the diagram.
So the bottom is a semi-cylinder, right? So you can see the bottom. So bottom is half cylinder of length L, and there is a partitioning. This is like a wall. Okay, this is wall. Okay, this is also a wall, and this entire system is hinged at the center. So there is a center hinge. You can see the black dot,
Yes, sir.
and about this hinge, it can turn the right to left. It can turn clockwise or anti-clockwise. Okay. So that is the whole shape. Again, 3D view will not be given to you, only 2D view. And now it is filled with, let's say, liquid water. If the radius of the semi-cylinder is r, the question is up to what height we must fill the liquid so that this shape remains at equilibrium. Got the point?
Yes, sir.
So we have to find the H value for the equilibrium of this. Basically, it's a flush system. So the moment water will exceed certain level, it will turn down, and water will leak out. So you can think this way. So it's a kind of some sort of maybe sensor, something water sensor. So if the water is filled to a greater height, then it will remain, because this is like a stopper, kind of stopper. So it cannot turn like clockwise. It can turn anti-clockwise because this is wall which is stopping it. But that is not the question we are solving. We are solving simply question that for what value of H the system on the right will be at equilibrium. That's it. And on the left side we have a wall so that the water cannot leak out. So that's the only purpose. So I hope this is clear. I hope this is clear.
Yes, sir.
Done, guys? Okay. Look at this. So we know that about the center. So if I draw this FBD, so water on the vertical wall will apply force somewhere here, right?
Yes.
And if the height of water field is h, then we can say this must be h by 3.
H3. H.
But at the same time, water is also applying force at the base here. And because the base is having same depth, we can say the pressure must be same, and therefore the center of pressure will be exactly at the midpoint. So the center of pressure at the bottom is R by 2. So we can say the wall pressure is F1 and let's say the bottom pressure is F2, which is acting at R by 2. And the torque due to these two forces about the hinge must be 0. Okay. So torque about the hinge, we have to just make this torque 0. And if you do so, what will get? F1 multiplied by h by 3 equals to F2 multiplied by
R by
R by 2. And F1 formula we know it's rho GH square by 2 into L. I think so, right? So it's rho GH by 2 into, yeah. And then F2 will be, so the pressure at the bottom is rho GH. And the area is RL, the base area into R. So we can cancel out rho GH from here. L will cancel out from here. 2 will cancel out from here. So what we are left with is h square by 3 is equals to R square. H turns out to be root 3R. Is this clear?
Yes.
So when it comes to torque in a liquid, and why we are applying torque? Because of the obvious reason. We are not aware of the hinge force, right? So hinge forces are known to us. So the only method to solve this problem will be torque method. So we are applying torque about the hinge and we are putting to 0. And this leads to the answer h equals to root 3. It means if you fill the water at root 3 r, r height, then the system will be at equilibrium, so that clockwise torque and the anti-clockwise torque will balance out. So now let's say the water level is less than this value. If water level is less than this value, then what will happen? Which force will be dominant? F2 will
F1.
be F1 or F2?
F1.
F2.
F2. If F2 value, then F2 will be bigger value than F1, and therefore it will open. So you may create some sort of sensor here, that very delicate sensor which can detect the water leakage or not, or based on the water leakage you can say something. So maybe I can put some potassium below the leakage point, and if the water will leak out, then potassium will burn actually, and some fumes will be produced. So anything we can create. Okay, so we can make some sort of device also. So buoyancy is used for the like in flush system, in cisterns, various things like this. Okay. So there was a JE problem. Let's do this problem. So in a glass tumbler, we have some amount of liquid. As you can see, dimension of the glass is given to you. So if I divide this liquid into two equal parts from center, or you can say if you think that this liquid is having two separate half cylinders stacked together, the question is, ignoring the surface tension, what will be the force of one half of the liquid on the another half? That's the problem. Find the force of one half of the liquid on another half, ignoring surface tension. Done, guys? It's the same answer because if you cut into two halves, you can see a flat surface, and we know the pressure distribution on this surface because pressure will follow the same formula rho gh, right? So it's the same answer. It's nothing. It is simply rho g h square by 2 into width will be 2r. That's it. So the answer is. So if you cut it from here, into two halves. Not what it is. So this is the flat surface you can see, and the surface will have the width 2r and the height is h. And you're supposed to find the force on its surface only, and that is simple because the pressure distribution we know, and we know how to find the force, which find the pressure at the center, which is rho g, h by 2, and multiply with this area, which you can see, which is h into 2r. You can do this way also, it's the same answer. Now, what happens if we include the surface tension? So, what if surface tension is also present? Surface tension is T. So, what is the force on 1 due to 2? Tell me, guys. So, the pressure will push the other part or pull the other part?
Push.
And surface tension?
Pull.
So, if you draw any half portion, then there are two forces it will experience. One is the pressure, which is the F1, but the other half will be pulling this part. Surface tension acts as a surface, and this pull force will be how much? T into 2r. So the net force will be how much? Rho g h square r minus 2tr. Is this clear? So the pressure is
Yes.
pushing the surface tension is pulling it. So that's the answer. And this is exactly the sorry, the J problem. So J did ask for the surface tension and the pressure distribution. So you can think these two are separate forces. One is pushing it, another is pulling it. So the net will be the difference of the two. Okay. So let's do this problem. So we have a cylinder here, and it is completely filled with a liquid of density rho on the left side till the top, and on the right we have a denser liquid which is of density 2 rho. So the question is how much we must fill so that cylinder remains at equilibrium.
This is the 2 row part.
Yeah. So for equilibrium, sorry, find H. So the row will push towards right, na? So 2 row will push towards left. So the question is, if you feel equal height, then 2 row will be dominated for sure because it's double density. So you're supposed to feel less than the first liquid, right? Because we want to equate the forces. So for what height we must fill in order to yeah, do this. Question is clear?
Yes, sir.
Yes, sir.
Go ahead. So you need not to worry about the shape. What you can do is just imagine a flat surface equivalent of that shape, like projection, and think of force on that surface. That will give you the same answer. Because the entire system is in equilibrium, which means this trick. So if I draw a flat surface here, I can see the liquid here is also in equilibrium. This is also in equilibrium. Everything is in equilibrium, right? So the force on the flat surface will be same as the force on the cylinder. Correct? Because everything is in balance. So we need not to get worried about the curved surface. We just make a flat surface and we can think that, okay, how much force the liquid will exert on the flat surface. Understood? So this will experience the pressure like this on the flat surface. And because everything is in equilibrium, so the same force will transmit to the cylinder also, right? And same thing here. H2. So it is like we are equating these two areas. Because the net force will be equal to the area under the curve. So the base will be here how much? Rho g 2r. And here the base will be how much? 2 rho gh, right? And because this is the load diagram, so the area of the load diagram must be equal for the force to be equal for the everything to be equal, right? So you can do by the same basic method that you know how to find the net force on a given surface, and you can get the answer. So let me solve this quickly. So on the left side, the pressure at the center of the flat surface will be rho g r, and the area will be 2r into whatever is the width, which you don't know. And on the right side, we can see the pressure at the center will be 2 rho g h by 2, and the area will be h into L. That's it. Okay, this much. I hope this is clear.
Yes.
Now the another question is it possible for the liquid to, sorry, is it possible for cylinder to rotate, or will it rotate here? Yes or no? Will it rotate?
Yes.
Okay, the answer is no, it cannot rotate because the liquid always exert force normal to the surface.
Sir, but
If you think, no, don't look at the pressure distribution, look at the actual force acting on the cylinder, and the actual force will be due to the liquid in the contact. And what we
Also, it
need to
will be
remember,
towards the center every of
yeah,
force.
correct, correct. Because every force is towards center, so there is no torque. So that this is the confusing part. Like when we analyze the force, we write the pressure distribution and maybe multiply with the area. Because the force, if you look at the force projection wise, it will give the same answer. That's why, although it's acting radially, the force always acts radially, because if you add all the radial forces, it turns out to be a projection actually. So this is a projection problem, and therefore the answer remains the same. And that is why, like, it will fail to produce any torque because the force is always radial at every point on the cylinder, and radial force will pass through the center because that is a property of liquid. It always acts normal to the surface in contact. So that is, you have to keep in mind that while solving the conceptual question, although we have a force balancing here, just so although we have a force balancing here, but there is no torque actually acting. Yeah, on cylinder because of the very property of liquid pressure. Hmm? This is the challenging part which you need to remember. Is this clear, guys? The
yes.
property of liquid always acts perpendicular to the surface. So now we need to solve one question from IITG because that's very, very important. Uh, so the buoyancy always gives the wrong idea. So it's good to think of pressure and area. That's it. So I need to search for that question from J. Maybe I should find. Hmm. About this question. So although I have shared the entire, but right now I have also shared one page. You guys can see this page actually. It is getting downloaded. It's too much. Okay, I hope you receive the page. And there is something with comprehension based question. You can see that. Can you read this question? Passage 1.
Yeah.
Yeah. So you're supposed to solve passage 1. So you can zoom the diagram. Hopefully you can see the diagram. In case if it's not visual, let me know. So as I said, in JEE, they will only give you the 2D figure and you have to figure it out like how to think in 3 dimension. That is very, very crucial aspect of solving problem. I think this is better visible, right? You can see now. So questions clear, guys?
Yes.
So the passage 1 we have to do.
Yeah, passage 1.
Yeah, so
So the first question is on the first page. Actually, first question is on the right side. Actually. Yeah. Then second, third question is below. So if you read the first part and then this diagram part, you can see the diagram clearly. So try this question, then answer. This is very crucial question.
So the forces will act on the remaining surface area of the block.
Pardon?
The forces will act on the remaining surface area of the block.
Yeah, whatever is in contact that will experience the force, and the force will be pressure at that location into area. That's it. And the property of pressure is it always acts perpendicular to the surface. So
Perpendicular.
the top surface will have the downward pressure, but the bottom will have upward pressure. And then to lift off, the net upward force must be balancing the gravity, the mg, correct?
Yes.
And to find the mg, we can use the density and the volume relation. So that is what you have to do, and that's pretty much easy. Just think of equilibrium question of gravity versus pressure difference
For
and all.
H1.
Yeah, so you have to take each case separately, read the question carefully, and then write the, FBD, draw the FBD, and then write the equilibrium equation, you will get the answer. It's pretty easy to answer, just you have to write carefully. So this tests your patience of writing. Try this out.
So how to solve the third one?
Pardon?
How to solve the third question?
So you got the answer for the first two?
Yes.
Very good. So you got the answer for the first two questions, right?
Now.
What do you saying? Yes, no?
Yes, yes.
Okay. Very good. So do the last part.
Sir, can you solve the third one?
So in the third one, what they're saying? In the third one, yeah. So in a situation two, what is situation two? I don't know. For which the block remains in its original position without application of an external force. So find the height of the water S2. So what is S2? So that's fine. No? So if you if you fill the water below the H2 is given in the figure, yeah, that's fine. So the only pressure will be bottom, not the top, right? Understood.
Yes.
So the only pressure is from bottom. So just you can add the bottom pressure will be how much? Rho GH2, correct?
Yes.
Into the whatever area is exposed to.
12 hours.
Yeah, so that will balance the mg. Okay. So what they're asking, what is the so if H2 is more than certain value, then it will again float because the pressure will lift off. So you have to drop the H2 value so that the pressure is not good enough to balance the weight. So this is what they're asking. I hope so. If you read the question. Yeah. So in situation 2, if H2 is further decreased, then so if H2 is further decreased, then it will never go up, no? Because if it is balancing at H2, going further down means it will not be able to push enough to lift off, so it will remain there only. So A is correct. No? Now for the other part, let's if H2 is this much, cylinder will again start moving up. So to move up, the buoyancy and the weight should be equal. So that will give you the H2 value. You can do it this. I think you will get some value H by 3, whatever H by.
Sir, 4h by 9. H2.
What?
4h by 9. H2.
Yeah, 4H by 9, fine. So for anything below 4H by 9, we'll keep it there only. Understood? No matter where you take. So that's a simple answer. Sorry. Okay. So that's the answer, no? That's it. So this is from J. Which year it was asked? 2006. Oh. All right, guys. So let me do something new. So solving the question of fluid is as good as solving the laws of motion. The only difference I said, writing the ability in terms of pressure and area and so on. So whenever it comes to liquid, don't write the weight of the liquid, just write the pressure into area and you will be good with solving problem. Next part of the problem, I mean, sorry, the theory is called I think buoyancy. So buoyancy is pretty much a straightforward thing. We have already discussed. Sorry. So there are many ways in which you can think. The best way is in terms of laws of motion. So imagine we have a liquid here, filled with helium. So imagine a layer somewhere here. So you can see there is some water above this layer, correct? And some water is below this layer. I hope I'm audible to you guys.
Yes.
Am I audible? Sorry. Okay. So now, if you think of this part and if you do the ABD, it will express mg below. So the obvious question is, who is stopping this part to go below? So why this is at equilibrium? That's the question. If you consider this as a system, then why this is at equilibrium? So we can say that okay, the liquid below it is exerting some force, correct? Please switch off whoever is. Who is there? Mute yourself, whoever is. Okay. So we have a liquid and this is under gravity, but the gravity is pulling down, it is not going down. So we can say that okay, the remaining liquid is stopping it. Think in this way. So we have a liquid. And so now I'm considering this part of the liquid, which is part of the liquid itself within the liquid. So it will have its own weight. How much will be the weight? Let's say the weight is density, volume. So if I consider a small portion of volume V, then I can say the weight is rho Vg, correct? This is the weight of the liquid, which I'm considering in the this entire vessel. Now you can see that even this liquid is at rest. So how much force we need to apply to keep this at rest? So answer is rho Vg. Now this is due to gravity. But who is applying this value? So this is applied by the liquid action. And therefore, the force that the liquid is applying in the upward direction to hold this liquid there, this we call buoyancy. Understood? Am I audible, guys?
Yes, sir.
So you can see that the weight of the liquid is balanced by the force due to liquid, and fortunately we are naming this force as buoyancy. Okay. So the obvious question is, this is the force that is a natural ability of a liquid to apply. So this is something natural ability you can talk about. Now imagine in a scenario 2, let's say we have a different scenario here. And now what we are doing is, so instead of that volume of liquid, we are putting something else. So we are putting something which is much more denser than liquid. So now in the same volume V, in the same volume V, what we can realize. So if the volume I keep as V only, liquid is not aware of the fact that it is now replaced by something new object. So what liquid will do is it will just look at the equivalent amount of water that would have been present in that volume. So in a V volume, if the amount of water is V, which is possibly present, and that is now replaced by something new, so the buoyancy force will be same as what liquid is capable of, rho Vg, where rho is the density of liquid. But at the same time, the gravity will now apply force mg on the object, which is different from the earlier value. So earlier it was liquid, same liquid, so the buoyancy was and the gravity was balancing out each other. But now we have two different values. One is the buoyancy, other is the mg. If I say the density of this object d is bigger than the liquid density, so definitely the downward force is bigger, right? And if the downward force is bigger, it will sink. I hope this is clear to you guys. It's clear.
Yes.
So if the density of the liquid is more, than what will happen? Sorry, if the density of the object is more than the liquid, then the gravity will dominate. Buoyancy is acting, but it is not able to balance it out, so it will sink. Now, if the density is less than the liquid density, if d happens to be less than rho, in that case the buoyancy is definitely much more than gravity, so it will go up. But in the process of going up, something will happen. What will happen? So in this process, this object will try to go up, will reach the surface, and will try to also go out of the surface. And now, because the buoyant force is much more than gravity, so it will only sink that much, that the buoyancy force on this part of the liquid, which is called the submerged volume, which is less than the actual. So now gravity is acting mg only, but we need less buoyant force to balance it out. So only partially the body will get submerged, not fully. And now the volume which is within the liquid will create enough buoyant force to balance it out. So anything which is lighter than the liquid will only partially submerge, not fully submerge. So if it is equal or more, it will submerge completely or go inside. If it is partially, I mean, if it is less denser, then the buoyant force that we need to balance out is definitely small. So it will submerge only that much which can balance its weight. Understood? Is this clear, guys? Yes or no?
Yes.
So that is the intuition of one force. We'll see some more technical difficulty with this definition. So first of all, we'll add the very famous Archimedes principle. The Eureka moment. There's a famous legend. So you said Eureka, Eureka. I got it, I got it. So Archimedes principle, what it says in a simple layman term, that And remember that this principle was given much before, or you can say even in fact um, thousands of years, not roughly 2000 years before Newton was born. So you can imagine the genius level of Archimedes much before the science took any form on Earth. So mostly that time it was only philosophy and intuition. So there is no mathematics. So when whenever whenever a body is either partially or fully submerged inside a liquid, then the net upward thrust called buoyancy is the net upward, put in bracket, the net upward thrust acting on a so net upward thrust acting on a body is equals to is numerically equals to what? Weight of the liquid displaced by the body. So how much you displace the liquid, that will matter, nothing else. So is it possible for a body to displace more than its own volume? So however you may submerge, but you cannot displace more than your own volume, isn't it? So there is a limitation to the buoyant force of a body. It is equals to the total volume of the object. So if we have a liquid and if we have some object, so this is the maximum possible submersion, right? And if this volume submerged is V, so the weight of the liquid displaced by this object is how much? So you can see the V is the liquid displaced, volume displaced. So volume displaced multiplied by density of liquid multiplied by G, because weight equals G. Okay, so the buoyant force turns out to how much? V rho G. So now this is always true, because if you have partial submersion of a body, then the V represents this part. So this is the V part.
So
Yeah.
the buoyancy force won't act on the center of mass, or will it act on the center of
No,
mass?
no, it acts at something different. That's called center of buoyancy. We'll talk about that called meta center after a while. So that is the topic of this ongoing buoyancy. So the buoyant force is called V rho g. So you can think of center of buoyancy as the center of mass of the displaced liquid. That is, you can think of. So if you look at this part, let's this case. So the liquid, if you think of the liquid displaced in terms of shape, this is the liquid displaced, right? So it will have some center mass. That center mass is called center of buoyancy or meta center. So there is a name for this, meta center or center of buoyancy. We'll see that. Don't worry. So if it is completely submerged and if it is having the uniform density, then you can say that center mass and center buoyancy will be same actually. Okay. So for example, if we have a cylinder like this, and if I completely submerge it, it's completely in the liquid. Then the liquid displace is also the same cylinder, and the object is also the same cylinder. So center buoyancy will be
The mass
center of the liquid displace, which is fortunately the center mass of the body, if it is uniformly dense. But in case of partial submersion, the center mass of the body is here, but the submerged length of the cylinder is this much. So center of mass is here, but center of buoyancy will be midpoint of this submerged portion, which may be somewhere here. You can see we have two different values. So it could be same, it could be different. We cannot guess just like that. Okay. Anyway. So the bond force is very much simple, V rho g, but there's some catch to write this formula. So this formula is not always true. I mean, what we need to remember is, for bond force to formula to be true, we need to have the bottom of the object covered by liquid layer. So we should have at least one layer of liquid here. Because if I remove this entire layer from the here, the upward force will stop, right? Because we know that liquid will only apply the upward force. No? That's the reality. So let me give you a situation where this formula will be invalid. And this is not the basic formula to apply anywhere. So it's good to think of in terms of pressure that will give the right answer. So imagine we have a vessel like this. And we have a block actually. So listen, the block is completely pressed on the surface. And then you start pouring the liquid. Okay. So now you can see this is a liquid, and the volume of this liquid is this object is V. So can we say the bond force is V rho g? Yes or no?
So can I repeat the question?
Question is, you can see a block at the bottom, right?
Yes.
And there is no liquid layer from at the bottom. So it is completely pressed. So the liquid is squeezed out. Or maybe it's not present at all. So no liquid here. No liquid layer at the bottom. So the question is, will there be any bond force on the block? Yes or no? Will there any be bond force? Yes or no?
Yes, sir.
But the bond force is the net upward thrust, na? So from where you can get the upward force? So if you look at the liquid surrounding this block, the only force I can see is like this and like this. So who is going to lift this block? I don't see any force present to lift this block. So liquid is acting from top, from the left, from the right, from the front or from the back, but not from the bottom, right? So there is no bond force. So the bond force is zero actually. Bond force is only expected or only written when we have the layer present below the surface. So this portion must have the liquid layer at a single layer. Then only bond force you can think about. So a single layer is capable of creating the enough pressure to lift this block. You can do this experiment easily if you have a really flat surface. So you can take something like maybe you can take something what we say okay, a vase or something, or if you have a cube at home, glass cube, you can put it. So put on a like plain plate, a plate which is plain. Pour the water if you have enough depth, or if you have a bucket, and then you can try to lift the block. It's really difficult. So you cannot lift vertically. It is impossible to lift vertically because the pressure is too much. So what you can do is you can slightly tilt left or right. So once you tilt, then liquid will enter the bottom and will create the exert the pressure to lift easily. So buoyant force is not only the formula V rho g, where V is the submerged volume. This is more than that. We need to have the liquid layer below the bottom. So therefore, if there is no liquid layer below the bottom, we cannot think about buoyant force. In fact, we should not write buoyant force. Okay, is this part clear? So here the buoyant force is zero. Understood?
Yes.
Hello, hello. So there is no buoyant force. Okay. So next is okay, some problems. Let's do some problem. So we have a liquid, and this is very interesting. So the height of this, so imagine this is a cylinder of height capital H, and it is floating only by submerging small h. So if this is in equilibrium, so what we can say about the density of liquid versus density of cylinder? Do we have some relation between these two? And because in this case you can see cylinder is completely, it is inside the liquid and bottom is also having liquid. So now we can think of the upward thrust. So the question is, can we write the force, draw the ABD of this cylinder? So if you draw the ABD of the cylinder, how it will look like? So let's say we have a cylinder, and the cylinder will have some cross-sectional area, which is generally not shown in the figure. That's very common practice actually. So let's do the ABD. I make a habit of drawing this ABD always. So in ABD, the below force will be how much? the weight of the cylinder. And if you write the net upward force due to liquid, the net means including all places it can act. So the net upward force in this case we can write as buoyancy. And how we write the buoyancy? So volume of the submerged part, and you can see the volume of the submerged part is only up to this value. Okay.
Yes.
So put this into mathematical form and we'll get the answer. So AB equals to mg. What is AB in terms of cross-sectional area, height, whatever you can write? So to solve problem, you will learn this part, that you assume the area of cross-section as A on your own, and then try to write the volume. So what is the volume submerged? Tell me, guys.
Small h into L.
So what is the bond force? V rho G. Correct?
Yes.
And what is the weight of the cylinder?
A into capital H into D.
So A into capital H into D is the mass into G, correct? And you
Yes.
can see that
Yes, sir.
whatever we don't need will cancel out. So A will cancel out because A is anyway not given. And the ratio of height is small h upon capital H is same as D by rho. So basically the volume ratio, the submerged upon total, is same as the density ratio. And here, because the cross-sectional area was equal, so luckily we got the height ratio as the density ratio, because volume will be proportional to height. So in reality, it is the volume ratio which is same as the density ratio, not the height ratio. And because the cross-sectional area was equal, or was same throughout, so we say that the height ratio is same as the density ratio. So only by looking at the diagram, you can tell me the density of the two, liquid and the object. And so if you know the density of the liquid, you can find the density of the object just by this relation. So if you can see that something is floating only half submerged, you can directly tell that the density of the object is exactly half the density of the liquid, because the cross-sectional area is same. So this is something interesting. Now there is a very famous question that is generally asked. So this is the initial value. This is equilibrium. How much extra weight we must put on the cylinder to make it completely submerged? The minimum value. So let's say call it question number A. I don't know. And then we can solve like this. In the previous question, find the minimum mass that must be put on the cylinder to make it completely submerged. So how much we have to put the mass
A
over this?
small h rho minus A capital H D.
Yeah. So the m will be equals to
A small h rho minus A capital H D.
So H minus H. Now how you writing? This much only, na?
Huh.
Yeah. So the answer is very simple. Look at this question carefully again. Tell me, guys, if you submerge the remaining part which is above, will it create extra buoyancy? Yes or no?
So the submerged part.
No, no, no. The part which is above the liquid layer, if you put it down, so the bond force will increase. Yes or no?
Yes.
Yes, sir.
So by what amount the bond force will increase?
The weight that
The extra volume which you will submerge, which is the volume above the liquid, which is H minus H into A, right?
Yes, sir.
So that V rho G will be the extra bond force. So we need to put the mass which will balance the extra bond force. So that will be, no, what I'm writing. Now G will not come. This is mg equals to this, so G will cancel out. So M will be A into. So you can think this way. So now the cylinder is completely submerged. The whole H is here, and we have put some mass just to manage. And if you write the equilibrium, so what you can write? So the downward force will be M plus the mass of this object, which is AHD. So M plus M whole into G equals to the bond force, which is AH rho G. Understood? So M turns out to be how much? AH rho minus D. And if the D was not given, we can convert from the earlier equilibrium relation. So from earlier equilibrium condition. So from the earlier equilibrium condition, what we can write?
rho by d is equal to small h.
H by H equals to D by rho. So basically, D into H you can also replace by rho into small h. So you can put it here. So M turns out to be AH rho minus A rho is small h, and therefore the answer is A rho into H minus. So there are multiple ways in which you can express the answer depending on what is given to us. And the best way we could have solved is balancing the extra buoyancy that will be produced because of the extra displacement of the liquid with the added mass. So the thinking will be up to you. You can think the way you want and you can solve question like this. So there is very famous problem that is always asked. So again, so imagine the same cylinder, small h, capital H. And right now it is at equilibrium. So right now it is at equilibrium. Okay, have we done the HM part? No, no.
No, sir.
Okay. But the question is, if I press it slightly below and release, then will it oscillate? Yes or no? So if you press it slightly below, then bond force will be extra, and then it will throw it up. So in a way, it will oscillate. So the question is, find if the cylinder is pressed so if the cylinder is pressed slightly and released, then it will oscillate. Find time period of oscillation. And now this is easy. So although I haven't taught you the HTM equation, but there is a very finite steps. If you follow, you will get the answer. So let's say you first of all press by some value. Let's name it. So let's call it X. So this is what you do. Then find the extra force, or called the restoring force. So if a restoring, which is always the net force. So we know that this extra push will create extra bond force of value V rho G, and this is going to restore back to the original position. So we call it a restoring force. And we write acceleration as minus F restoring. So upon mass. Why minus? Because the displacement and the acceleration are opposite. So it will try to go up when you try to push down. So the tendency of acceleration is upward. That's why we put a minus sign mathematically. So minus AX rho G by M. M is the mass of the cylinder. And we know that mass of cylinder we can write as A. So A turns out to be minus rho G by HD into X. Okay. Yeah. Fine. And we know that DH is equals to rho small h, right? If you remember, like h by h is how much? D by rho, correct?
Yes, sir.
And if you substitute here, so DH is h rho, so you can write. And the rho, it will also get cancelled. So what is interesting is the answer has nothing to do with anything. It only depends on the initial value. So this is minus G upon small h into X. And small h is called the equilibrium depth, or okay, whatever. And now from the theory of SHM, we compare this with a very standard formula, which we write as omega square x. Okay, that we'll learn later on, don't worry. And then we compare the omega square, which is G by H, which gives the value of omega G by H, and the time period we write as 2 pi by omega. And don't worry if you don't get it anything. And this is the answer. So once you will study the SHM chapter, this whole thing will make sense. Just put it in for the sake of content in your notes, so you can learn, understand later on. Okay, no problem. Okay, I will not take much of the SHM problem here. That I'll keep for the SHM chapter.
Omega square x is a formula for oscillation.
Pardon?
That pendulum oscillation.
Yeah. It's similar to the pendulum, which is having formula 2.0 L by G. Here L is like replaced by the small h, which is the equilibrium depth of body. Okay. Okay. next part. So after this, what we can do is, yeah. So derivation of buoyancy using Pascal's principle, and this is what we actually use for solving problem. So in most of the question, you are not supposed to even understand buoyancy, just use this Pascal's principle, you get the answer. But in some scenario, buoyancy is really useful. So we'll see how to make the most of it using the Archimedes definition and the Pascal's definition. So what Pascal said is simple. So let's say we have an object inside liquid. And the top layer of the cylinder is at some depth, you can call it, let's say, H. And this is capital H. Okay. So if you want to find the buoyancy is the force due to liquid, and it is a net upward force. So let's draw the FBD of this cylinder. And in this FBD, only write the liquid force, like force due to liquid, not the gravity or tension or friction or spring or whatever. Only force due to liquid. So there are three types of forces that we can explore. So the first is the force on the side walls. So of course, this is difficult to draw from all sides. I will do from the two sides just for the understanding. Then the force will be from the top and bottom. This is the side wall. And what you need to remember that whatever be the shape of the object, the net horizontal force on the body is always zero. So this is what you have to believe, because object cannot move sideways in a liquid. It can go up or down. It cannot go right or left. If you drop something in a liquid, it will not go left or right. So what we say is that the net so net horizontal force sorry. So this is what you need to remember. The net horizontal force due to liquid is always zero, no matter what's the shape, irrespective of shape. So this is the first point you need to remember. Now comes the other forces. So the top will apply some force. Because it's a flat surface, we can add the force easily as pressure into area. The real problem comes when the surface is not flat, because in that case it's very difficult to write the force. And because the depth is very much known to us, which is h, so we can say this, the pressure here is rho gh. and let's say A is the area of cross section. Okay. The same liquid will go below, and you can see that I'm using the longer arrows to demonstrate that this pressure is bigger than the pressure above. So bottom will always have the bigger pressure because it is at greater depth. So this pressure will be how much? Rho G H plus H, correct? Into area. So this is called the F1. This is, let's call F2. So the bond force is defined as the net upward thrust, and thrust is defined for the liquid, not for the other things. Net upward thrust. So in this case, you can write as F2 minus F1. That's it. And this turns out to be rho G capital H into A, correct? And if you look at the volume V, is nothing but A into H. And that's how it turns out to be. So you can realize that this is V rho G is the bond force formula. And we need not to actually think of Archimedes principle. We can just look at the upward force and the downward force and things like that. So the difference of the two, the downward and upward, will be always equal to the bond force. So bond force is the alternative. If you know there is a downward and there is a upward force, you can always invoke the bond force formula. When not to invoke the bond force, imagine if the bottom having no liquid layer, F2 will vanish. Then is it possible to write the FB equals to minus F2? The answer is no. In that case, the object will be only pressed down rather than going up, and therefore the net upward force will vanish, and therefore you cannot think of buoyancy. Is this clear?
Yes, sir.
Just is this clear, guys?
Yes.
No. So look at this problem. So we have a cylinder which is very heavy, maybe, and it is suspended with the help of thread. Yeah. Okay. And it is completely filled inside the liquid. So I need to be careful to draw this. Okay. So this is height h. Now what I do is I will do something at least. So I remove a part from the bottom. So I exactly remove the hemispherical portion from the bottom, as you can see. Mhm. Yeah, no, I think it's fine. So you can see that a hemispherical portion is removed from the bottom of the cylinder, and the radius of this hemispherical portion you can think as same as the radius of cylinder, which is r. And the height of this the entire cylinder is given as. Now the question is interesting. As you can see, it's completely submerged in the liquid. The question is, what is the force due to liquid at the bottom only? Now that's interesting. Find force at the bottom of cylinder due to liquid. So you see, neither I'm asking the buoyant force nor the pressure. I'm asking only how much force the bottom is experiencing because of the liquid, because this is filled with liquid, right? Yeah, so there is a liquid here. I mean, I should have mentioned the liquid. Yeah. So now liquid is completely occupying here. This space. Yeah. So if you want, you can try for a while. Then also think about
Can you see the previous page?
just. A minute. So this is the formula you have to use. The bond force is always the difference of the two. So if you use this, you can get the answer. That's a trick actually. So you employ the Archimedes principle and the Pascal's law, and the Pascal's principle you can say here, and just bring these two together to get the answer. So one will help you getting the other answer. So because of the two equivalents of writing the same thing, we have this flexibility of getting some answer which are not very much direct answers and difficult to find otherwise. If you do the integration and all, that's kind of very difficult. Done, guys?
It's the last step. Done, sir.
All right. So I think you must have written F2, which is the bottom, minus F1 is known to us, rho G H pi R square, right?
Yes.
And this must goes to bond force, which is volume submerged, which is pi R square capital H minus
Minus
2 by 3
pi
pi R cube. Very good. Pi R cube V rho G. That's the answer.
Yes.
So this was a JE problem, a J advance. Okay. So you can solve any problem like this because we have two equivalents of same definition. One is the Archimedes principle. The only like caveat in the Archimedes principle is do not apply that formula if you do not know the reality of the situation. It means if you know, if you are sure that the water is or not water, the liquid layer is present at the bottom, apply it. If it is totally absent, do not apply it. But then comes something in between, like neither the left nor the right. So imagine a situation. This is a very dangerous situation. So generally, if you have any vessel, maybe a vase, which you call lota, of shape like this. So if you have some object like this shape, with flat bottom and then curved surface, okay. And if it is filled in liquid, yeah, right, like this. So you may think that, okay, of course there is no force from here. So let's say there is no liquid layer, no layer of liquid. So of course bond force is not present, but the good thing is we have something. And the liquid layer can have some upward component possible here because of the shape. Okay, so some bond force will be there now. Now I cannot say there is no bond force. Earlier it was not possible for liquid to have the upward thrust. Now I'm giving the shape in such a way that which will at least facilitate the upward force into the picture. So liquid can apply force like this, understood? And then force like this. And then force like this. So the question is how to find the bond force in this case now. I mean, what is the bond force acting now this? So from the V rho G part, you have to subtract the portion which is flat part, this portion. So this portion will experience the pressure from the top, which cannot be having any counterbalancing act. And therefore, the total bond force must be subtracted with this pressure into area part. Understood what I'm saying? So you write the bond force V rho G, but subtract the part which prevents the buoyancy. So this entire cylinder is preventing the buoyancy, isn't it? Do you realize this fact?
Yes.
So that kind of question will also come in. That's very difficult level of question. So what you need to do is, if you can see there is some portion which is not having the liquid layer, but we have some portion where the liquid layer is present. In that case, what we do is we subtract the from the net bond force, considering everywhere the liquid is present, we subtract the force that this contact is subtracting. So that's the whole idea. All right, guys. So this is how we think about solving problem in three situations. One, when there is no buoyancy because there is no upward thrust at all. In other case, we have the complete upward thrust, not an issue. Third is a mix of the both, the first scenario, the second scenario. And that's why it gets really difficult to understand buoyancy in situations like this. Questions like this will not appear anywhere in the JEE domain. Only if you go beyond the JEE domain, I would say up to Olympiad level, these things are very common. Okay. So keep in mind, if you're reaching that level, so let's say if you're solving a problem and if you come across something like that, you can ask me a doubt and then I can solve. So if I solve right now, it will be of no use. Okay. So next concept is what? In buoyancy. So this is one kind of problem. So let's do something very simple, conceptual question of buoyancy. So we have a weighing machine. So let me draw the weighing machine first. Just theoretical problems, like nothing to do with the physics. Common sense puzzle problem, we can say puzzles. Yeah, that's better way of saying. So we have a weighing machine. Okay, that's good. And then we have a vessel. Then we have a liquids also. Then we have uh, a bob also, which is suspended from the ceiling. Okay. Okay, so this is liquid and so on, so on. So right now, I mean, let's say there is no bob. This weighing machine will read something. So let's say R1 is the initial reading of the weighing machine. And this initial reading will be equal to the weight of the vessel and weight of the liquid, correct? Okay. So in a scenario 2, I wish we should have this copy and paste facility in Zoom. That's very unfortunate. We'll do the entire thing once again. And now we suspend the bob from here, which is completely submerged in the liquid, but not touching the bottom. Yeah, that we are making sure. So now the question is, if I do so, the reading will change, yes or no? R2 will be equals to R1, less than R1, more than R1. What do you think?
More than R.
Very good. So what is the extra value it will have?
The mass is given after that.
Let's say V is the volume of this bob, and it's definitely denser than the liquid, so it's getting inside. So can you guys tell me what is R2? So the moment you submerge something, it will experience the force due to the liquid in the upward direction. We call it buoyancy. And from the Newton's third law, the same force will act on the liquid below, equals to buoyancy. And that's why the reading R2 will be the initial plus the buoyancy. That's it. So the extra value is due to the buoyancy force. So buoyancy will have the component downward on the liquid, and that's why it will read on the weighing machine. So the difference is equal to buoyancy. That's interesting. Okay, now in the question, if I ask you, can you find the tension force? How much is the tension? So the tension plus buoyancy will be equal to weight of the pendulum, and therefore the tension equals to basically mg minus weight. Okay, so this is the thing you can do. Then we can talk about buoyancy in the accelerating frame. We'll keep the buoyancy in accelerating frame. So there are two types of acceleration, which we generally we consider vertical and horizontal. So as of now, we'll only keep for the vertical acceleration. Okay. So imagine we have an elevator. In this elevator, we have a vessel with liquid. Imagine we have some object, and it is now going downward with an acceleration a less than g. So because this part of the liquid is also going down with the same acceleration as the lift or elevator. So if you do the ABD, then mg. Now what do you think? The AB should be equal to mg or less than mg? For this liquid to accelerate down, the net force should be
So
downward, right?
SB should be less than mg.
Exactly. Because the system is accelerating downward, so the net force must be downward. And earlier we were assuming equal because it was not accelerating. And now I can say the mg minus the new buoyant force, which I don't know, is equal to mass into acceleration. So clearly you can see that the buoyant force will change the formula from mg to mg minus a, and m is anyway we know rho into v. So that's common sense. You can see that the g is now replaced by g effective, right? And in this case, the g effective comes out to g minus a. And therefore, if you go downward, the buoyancy will decrease. And for free fall, when a equals to g, the buoyant force will never develop, because to free fall we do not need buoyancy; it should go just downward. And you can also see the g effective is 0, and you can also see the f buoyancy is 0. So in a freely falling liquid, buoyant force cannot develop. I hope this is clear. Okay.
Yes.
This is very much straightforward. So you can do the laws of motion and you can get the answer. So if A is upward, in that case, the buoyant force must increase than gravity to pull it upward.
Yes.
And therefore, the answer is G plus A. And so the buoyant force formula will change and it will become rho V G plus A. So I hope this is very much straightforward. You can do these questions like this. We do have a horizontal acceleration that will cover in a separate discussion. So the next lecture is going to be the accelerating vessels, and we'll start a new ideas about those things. Okay. So after that, we can go back to the buoyant force in horizontal frame. So now with this knowledge, I think you can solve a lot of questions from any book, SC Verma. If I have shared the sheet I have shared, the fluid dynamics, yes or no? The sheet for the fluid I have shared. Okay. So give me just a moment, I'll share first. Okay, I'll send. I mean, I think there's a network issue. Anyways, I'll send. Bye and take care.
Bye.